Hello, I'm Michael O'Connell, and in today's video we're going to solve a material balance problem in which we have three interacting tanks. As you can see on the screen, I've made a diagram of this problem to help us get started, and there is one thing that I would like to emphasize specifically, and that is that the tanks are interacting. And what that means or implies is that there's some dependence between these tanks, and that is going to be our fluid heights. And we know this from Bernoulli's equation, which comes out of the idea that energy is conserved. And with that, fluids occupy the space of their container, and that is why, for instance, if tank 1's height of fluid is greater than the height of fluid in tank 2, you're going to have some flow through this pipe at the bottom connecting the two tanks into tank 2, if that is the case. So what we want to do at the start of this problem is model the interaction between these tanks. And what is that going to be? Well, that's going to be the flow. And I drew arrows to show what we have. And here is the problem description that was given to me. We have three cross-sectional areas that are given. Those aren't going to change. And all of this will become much more necessary when we use Colaboratory to actually solve this problem. And then the initial fluid heights for the tanks are also given. But what we are going to want to do first here is model the flow between the tanks. The other key thing to notice here is that we have some sort of flow that is coming in to tank 2. So let's just get started and derive an equation for Q12. Now, why did I do Q12? Well, what you could take this to mean is that this Q12 is going to be we'll derive an expression for Q12 that is going to model the flow of fluid from tank 1 to tank 2, meaning that if fluid flows from tank 1 to tank 2, it will be positive. Okay, so that's super, super important for us. So that is what I would like to start with. Obviously, we have the same thing with Q2 and 3, and then Q3 just goes out to the surroundings, and that's, again, from this third tank over here on the right. Now we're ready to write equations to describe the flow between our three tanks. And in this problem, they give us this very, very important statement here, which is the magnitude of the flow between the tanks is proportional to the square root of the difference in fluid heights between the pairs of tanks. That's obviously a huge mouthful, but that is based on Bernoulli's equation, which, as I said before, comes from the law of conservation of energy. And there is also going to be this proportionality constant between tanks 1 and 2 and tanks 2 and 3, and that is going to be 0.1 for both of those. And as it says in this sentence here for tank 3, which is draining out at height 0 here at the bottom to the surroundings, the proportionality constant for that is also going to be 0.1. So let's call that proportionality constant alpha, just to keep things simple and start with the first letter of the Greek alphabet. And then we are going to use this to guide our thinking to model Q12, Q23, and Q3. So let's start in this Word document that I tried to prep a little bit for this. So Q12, what is that going to look like? Well, as I said before, we have our constant alpha in front, and that's a proportionality constant, which means it's going to be multiplied. And then we have the difference in heights. Now, as I said before, flow from tank 1 to tank 2 is going to be positive. But this is going to be based on the height difference. And assuming that the flow is going to tank 2, we're going to want H1 in front there. So that is going to be important for us. So this will be H1 minus H2. And as our problem basically told us, this is going to be raised to the 1/2 power. Okay, so that's kind of what our equation looks like. And obviously for 2 and 3, it's going in literally the same direction off to the right. It's just going to be the same thing with different numbers, right? So that's what we would have for that. For tank 3, we're actually going to have something that's quite similar. The only difference is that it's not going to be dependent on the height of any other tank. It's just going to be its own height, moving down. Obviously, that's going to flow the fluid out the bottom there. So it's just H3 there. And alpha would stay. And then let me get rid of the 2 comma and the subscript there. Okay, so there are our equations for the flow. And the next thing we're going to need is an equation for the flow that I had going in to tank 2. What is that going to look like? Well, this question set before us gives us even more information. It says that using the simplest form of control for the fluid level in the third tank, which is going to be a proportional control, the flow into the second tank is equal to the proportionality constant, multiplied by the difference between the fluid level set point for the third tank and its actual fluid level. Okay, so we have some variables that we can use to write an expression for this Qn, for the flow of fluid going into the second tank. And it's all based on a set point that we put in for tank 3. So what this problem is telling us is that with these interacting tanks, we have a certain height for tank 3 that we want, and that's going to be 4 meters. So I'm going to call that HSP, just for set point, right? And the proportionality constant is 0.1. Once again, with proportionality, that means it's going to be multiplied, and it says by the difference between the fluid level set point for the third tank and its actual fluid level. Well, what's its actual fluid level? That's height 3. That's H3. Okay, that's the height of the third tank. So let's try to make an equation for this. What is this exactly going to look like? So this would be Qn, and it says our proportionality constant, they call it Kc. Don't want an exponent, we want a subscript there. So Kc times, and it just says the difference between our set point, and I said that was going to be HSP. We'll call it H3SP because it's the third tank that the set point is for. And then its actual height, which is going to be H3. Okay, perfect. So now we have 4 equations. We have an equation for each flow rate that we have in our diagram here. So that is an excellent start. The next thing we have to do is recognize that our heights are going to be changing, right? Once we start this process, we start putting in fluid to tank 2, everything begins and fluid begins moving around. And what this says here for part 1 is to derive differential equations to solve the fluid levels in the 3 tanks. Okay, differential equations. What the heck is that going to look like? Well, we are going to do this, as you might expect, tank by tank. So for tank 1, let's describe the material balance, right? In this case, we're doing with fluid, so let's use volume, right? We have some volume of fluid in tank 1, some in tank 2, some in tank 3. And we know that the materials have to balance. It's literally in the name, right? Conservation of mass. So for tank 1, we need to describe the flow rate, or the volumetric flow, that is going into tank 1. So what exactly is that going to be? Well, let's figure out what the volume would be. That's obviously the biggest thing. And then it's going to be for a certain time interval, but we'll worry about that in a second. Okay, so for tank 1, they gave us this cross-sectional area, 0.5, which I don't really care what it is right this second, but we know that there's some cross-sectional area. That's not going to change. And then we have the height of our fluid. So that's our volume. Our volume is the product of the cross-sectional area and the height. And that's going to be true for all of these. So if we're going to make differential equations for the flow for each tank, or going into each tank specifically, then let's make our left-hand side just that, and that's going to be the volumetric flow. Now, what is that going to look like? Well, that is going to look like the cross-sectional area, so for tank 1, we'll call it A sub 1, times the height. Now, as we said before, this is a differential equation, which means that we have a derivative in it, which means that something's changing, and specifically for us, something is changing with respect to time. Well, what is going to be changing? Well, they told us that the cross-sectional areas, well, those are given, so those aren't going to change. They kind of give us a clue because they tell us the initial fluid heights, which implies there's a final that's not the same. But logically, as I said at the very beginning of this video, we know that the height is going to be changing by Bernoulli's equation. So that's our differential term. That's our derivative that we want here. So obviously, ooh, they have a little derivative symbol in here. Maybe I should use that. I had to change my letters though. That's okay. But this would be dH dt, right? Okay, so that's our volumetric flow rate going in to tank 1. And then everything else here is going to look very similar, right? And then I guess the one thing I forgot here is that these should have the proper subscripts, so I'll throw that in there as well, just so nobody gets confused. So obviously, they're not going to be the same until they reach steady state, which we'll talk about that soon enough. But let's see what we want to do next. So we have all our left-hand sides. That's great. Now we need our right-hand side. Okay, so we're modeling fluid that is going into tank 1. Well, there's nothing going in up here, right? So there's only one way that we can have fluid go into tank 1, and that's through this bottom section. But we have our arrow, Q12, pointing to the right, going into tank 2. So this should be pretty easy. It's simply the opposite, negative Q12. And thank goodness I already have some of this typed out, so I know that can be kind of tedious to use equations in Word, but that's going to be our flow into tank 1. All right, now what about tank 2? What about tank 2? Okay, well let's do that. That's easy. We have fluid that's flowing in, right? That we're actually controlling. So we have Qn. Obviously that's going to be positive. Then, like I said before, Q12 is fluid flowing from tank 1 into tank 2. So that's going to be positive going into tank 2. Okay. And then we have Q23, and that's going to be fluid that's flowing from tank 2 into tank 3, which means it's flowing out of tank 2. So that's going to need to be subtracted. Awesome. Now we're down to our final tank, tank 3. Let's start actually simply. We know what's leaving. We know this Q3 is going out. But we know what's going in is Q23. So that is what our equation would look like there. Q23 minus Q3, right? Because if we look at our diagram, you're going to have flow coming in here. This is going to the surroundings. The surroundings is not just going to randomly somehow pump fluid back into there unless there's some ridiculous pressure difference, but that's not part of the problem. So there you have it. There are our differential equations. And now that we have those, and I'd like to just put those on the screen. So these three specifically, these are our differential equations that we're going to use. Now what we're going to do is actually code all of this in Python and Colaboratory. Before we start coding in Python, there's a serious error that I caught in two of my equations here, and that's my first two equations that are modeling the flow from tank 1 into tank 2 and the flow from tank 2 into tank 3. And you might be able to catch what's wrong with these equations. as I said, we're taking the flow from tank 1 to tank 2 to be positive. And what that means is that we're going to have the height of fluid in the first tank subtracted from the height of fluid in the second tank, and that's absolutely fine. The problem is that what if the height in the second tank is greater than the height of fluid in the first tank? Well, you're going to have flow from the second tank into the first tank. And that is going to be an issue for us because then we have a negative value in our square root, and then we have an imaginary value for our volumetric flow rate. But that wouldn't happen in real life. So what that means first and foremost is that this needs to be an absolute value. So let me change that. And as you might be able to tell, that's actually the exact same problem with Q23. It's the exact same issue. Because if the height of fluid in the third tank is greater than the height of fluid in the second tank, then fluid is going to flow into that second tank, right? So we have that taken into account. And this is great, but the problem for us here is that we also need to indicate the sign of our flow, right? Because if we have the absolute value here, so like let's say height 2, the fluid is 5 meters high in tank number 2, and then the fluid is 3 meters high in tank number 1. Okay, so the difference is 2 meters, but this is an absolute value. That's not going to be reported as negative 2 meters. It's going to be 2 meters. That's not good because all these sets of equations, all of this down here, especially at differentials, are based on Q12 being positive when we have flow from tank 1 into tank 2, and thus being negative when we have flow from tank 2 into tank 1, which means that we have to have a sign, right? We have to have a sign. Now, what is that sign going to be? Well, that sign is going to be positive if height 1 is greater than height 2, right? And so this is what we want. We want the sign of this difference. And as I said, this is going to be the exact same thing here for Q23. So fortunately, I caught that mistake before we started coding. Now we're ready to solve our differential equations in Python so that we can plot the change in fluid height for each of our tanks over time. So I have some imports up here that I'm going to talk about very soon, but before we do that, let's take a look at what this gives us. So there are some constant values that are given to us that we should put in. So first of all, our areas, right? Our cross-sectional areas for all of our tanks. So A1, A2, and A3. And that is going to be 0.5, 1, and 2. And the heights, I believe, are going to be the same thing. And then we'll also need this for alpha as well. So this would be alpha 3, and then we would have alpha 2 and alpha 1, and once again, that is this term here, that proportionality in front of this square root of the height differences. So that's what we have there. And those are all going to be 0.1. And we want to change these to H1, H2, H3. And I'm going to put, I guess I'll put a 0 in front of those because those are the initial heights. So I just want to make sure that that's clear, right? That those are our initial heights. We don't have to do that for the cross-sectional areas or alpha because those are constant. And so that is not going to be needed. We are going to run this for some time interval. We'll start at time 0, but let's put an end time, like 500 seconds or something. And I think that should be it. I think that should be good for us. The next thing we're going to have to do here is create a function that will have a return for our 3 differential equations. because that's what we're going to want to solve. And to do that, we're going to use solve IVP from scipy.integrate. And the first important thing to note here is that we have our dy dt set equal to our function, which takes in time and, it has t. So just some sort of independent variable first, and then your dependent variable. And this time is going to be a tuple, so starting from your initial time to the final time that you specify. And then it says there's going to be an array, okay, a vector array of your initial y values, and that's going to work perfectly for us because what's our dependent variable here? That is the height of fluid for each tank. So we have 3 of those. There are 3 differential equations here. So what is that going to be? Well, we will call this our right-hand side, right? And we have t and y. We'll just use those. But we need to unpack y because we have multiple things inside of it. If we just had 1, I could just specify it as the first value that we put in. But we don't want to do that because we have 3, right? We have 3 of these initial heights that are going to be coming in. So we'll just do h1, h2, h3, and we're unpacking y. Perfect. So that's a good start. What do we need next? Well, now we're going to need these equations here. Okay, we're going to need all of those equations. Specifically, what we're also going to need is to specify our H3SP, which is the set point for the fluid height of our third tank. So we want the fluid height of our third tank to get to 4 meters. That's what we want. We were also told that Kc was, I think, 0.1, and that is also known as a proportional gain, which kind of makes sense logically, because what this is doing in controlling the flow rate that we have that's going in to our second tank, we have some gain that is proportional to the difference between the set point that we specify for the fluid height in tank 3 and the actual fluid height in tank 3. So if you think about it, calling it proportional gain actually does make a lot of sense. So now I'm going to make equations for these, which are the equations that model our volumetric flow rates between the tanks. So what do we want to return here? Well, what we want to return is the expression that would be for dH1 over dt, dH2 over dt, and then dH3 over dt. Which is what is that? Well, that's the rate at which the height in the first tank is changing, the rate at which the height in the second tank is changing, and the rate at which the fluid height of the third tank is changing. So what that just means for us, and I forgot to change these subscripts. We have A2 and A3. We would want to divide each side by our area. So for our first one, this would be, let's see, negative Q12 over A1. And then okay, and I'm forgetting something. I'm forgetting Qn. I knew that when I wrote it. Just had that feeling. Qn. What is that going to be? That's going to be Kc times H3Sp minus H3. So the difference between our set point and the actual height of the fluid that is in there. Okay, perfect. See where this takes us. So we have all of that. Now the next thing we have to do is actually use solve IVP. And what do we need to put in here? Well, we need to put in our function. Then we need to put in our time span. So we'll start at 0 and we'll go to our end time. We need to put in our heights, which for us is going to be the initial fluid height in each tank. That should satisfy. Whoa! Whoa, whoa, whoa. Look at all this. Look at all of this. Okay. Okay, let's see what's going on here. Well, one thing that I did forget is I wanted to specify that I want to do the Radu. I don't know how to say that. Radu method. And another thing that I actually wanted to talk about was making the dense output true. And what that is going to do for us is when I do shift enter here, it's going to give us some information, hopefully. This worked properly, and I think it did. Specifically, this gives us solutions to our differential equations. So if you've ever taken a differential equations course, a lot of that when you're solving much more simple differential equations by hand, you have some solution where you have like y equals such and such. So you're getting some expression for your dependent variable. In this case, we have 3 differential equations. So we would have we would have an equation that models the change in the fluid height in tank 1, tank 2, and tank 3. So we would have 3 different things there. So we can grab this sole attribute because we're going to need that to make a plot of the fluid height in each of our tanks. And we'll call that sole. Okay, so now that that's stored, and let's create some time interval for plotting purposes, and we'll use our same time interval, right? So 0 to tn, and we'll space these out accordingly, right? Just like we always do, using numerical Python, linspace. How many points? 500. I seem to like that number a lot these days. Okay, so we're ready to go there. Now, what we're going to need is to, let's just H1 plot, H2 plot, H3 plot. Apparently I do not know how to use the shift key properly, but we'll set that equal to our solution, right? But we have to put something into that, right? We have to put our time values in so that we can plot these heights. Notice, again, I did 3 of these. That's super important. We don't just have one differential equation here that we're solving. We have 3, okay? And we have our plot there. Now we are ready to go. And hopefully I can do this right. I have trouble remembering the syntax for this, but yeah, fig equals make subplots, and then I think this is going to be fig dot add scatter. Okay, what's our x? Our x is tplot. Y is H1 plot in this case, right? Name H1. And mode, we want that. Lines. We want to see the lines here. Okay. And then we can just do that. Let me close my parentheses there. Okay. Everything seems fine. And we're just going to do the same thing for our other ones. So for 2 and 3 as well. And I'm really, really excited to see how this looks. And we do have a problem, as I expected. Alright, so what did I do wrong here? To me, it says there's no function. Well, the function I'm using is make subplots. And they're correct. There is no function. Because when you call a function, need those bad boys. You need the open parentheses. Let's see how that looks. That's much better. That is much, much better. So before we head out here, let's talk about this a little bit, shall we? Let me change my end time to reduce it. But as you can see, actually, there are some initial comments I can make since we have a larger time interval. We see here that it's pretty much straight lines, right? What is that called? That's called steady state. Whenever you hear the term steady state, what you need to think is that all derivatives with respect to time are zero. As you can see here, because your fluid heights are not changing. So this is pretty cool. I would say that the only annoying thing with this is, and let me shrink this interval a little bit, you know. Okay, we have this dip here, and this is H3, so our third tank actually goes down initially. So that means when we start this whole process, like stuff just goes flying out. That's kind of funny. And it seems that the height of tank 1 and 2 basically, I don't know, from my perspective, it looks like they're basically the same at steady state, which is kind of cool. But what's obnoxious about this is that, what was our set point? Wait a second. Our set point was 4 meters. That's meters, fellas. What is this? This isn't even 3. And all I can say about that is the problem when you are using a proportional controller. So that is just something that you have to deal with. And we can play around with this, obviously. We can play around with this KC value. We can make it 10. But, things get really unstable. We have 80 meters of fluid and then fluid going back into the nozzle that pumped in fluid into tank 2. Okay, so that's not what we want. But hopefully that just alerts you to the fact that simplicity isn't always great, because it can really limit your possibilities. As you can see, part of the problem with using a proportional only control like KC that was given to us in this problem is that we never actually reach our set point for the height of fluid that we want in tank 3 when we're at steady state. And unfortunately, I have to tell you that there really isn't any remedy for this, because as I was doing before, we can keep adjusting these KC values, but if we look at that, so like let's multiply it by 10, right? So we have a lot of fluctuation. This is going up to about 18.5 meters, which would probably be too high. But we get past our set point and then we get somewhere here. As you can see from what I was playing around with, we get closer to our set point when we increase the KC value. The problem is that these other flow rates, or the height in our other tanks are probably going crazy. They're way too high, as you saw when I had the KC value of 10. And we're not going to deal with this in this video, but the remedy for this is what's called a PID controller, and that's proportional integral derivative controller. And I like what this explanation has, actually, on Wikipedia. It's pretty good, because it says that the PID controller continuously calculates an error. And I just want to say, the error it's referring to is the difference between our set point for the height of fluid in tank 3 and the actual height of fluid in tank 3. That's what they're referring to when they say error. As the difference between a desired set point and a measured process variable. That's what I just said there. And so it applies a correction based on a proportional, integral, and derivative terms. What it actually does account for is what's called the integrated error. But again, that's beyond the scope of this video, but that is something that we could code that would be a remedy for our problem that we have, in which when we use what this problem specifies, which is 0.1, everything works great. Our graph looks fantastic. But our steady state, what do we have? I mean, 2.47 is our height in meters for the fluid in tank 3 when our set point is 4. I mean, you can always cheat and put in values to like change that a little bit in your equation, but that's not going to be helpful. In the real world, you're going to want to use a PID controller, and that will get you to your set point, which is really cool. So hopefully this video helped you understand what it means for 3 tanks to be interacting, and obviously why these tanks are interacting because of the connection at the bottom, right? So if I had a tank below tank 3 here, the height of fluid in tank 3 wouldn't depend on this 4th tank that's below it, right? It's all about the connections at the bottoms of these tanks. So hopefully this is a good example of a material balance problem, and it helps you grasp further understanding about interacting tanks and flow of fluid and conservation of energy, conservation of mass, all those fun concepts that you've learned in high school and into college. So I hope that this was helpful for you. Thank you so much for watching.